Let us discuss the directive influence of substituents in benzene ring. Now, we know that benzene ring or any compound that contains benzene ring can undergo electrophilic substitution reaction, and we discussed 5 electrophilic substitution reactions. So, if there is a substituent present on the benzene ring, substituent means it can be an alkyl group, nitro group, OH group, ether group. If there is a substituent present, then the substituent will decide what is the product of electrophilic substitution reaction. So, what do you mean by directive influence of substituent on benzene ring? That is, substituents when attached to benzene ring decide the product of electrophilic substitution reaction. The product formed depends on the nature of substituent present on the benzene ring. This is known as directive influence of substituents on benzene ring. So, the substituent present on the benzene ring decide the product formed. Now, based on this, we can classify the substituents into 2 types. First type is ortho-para directing substituent and second is meta-directing substituent. So, the first type of substituent is ortho and para directing substituent. Ortho and para directing substituents. Now, from the name itself, these substituents, when they are present on the benzene ring, they will attract the incoming electrophile to ortho position and para position. So, we get 2 products. If the substituent is an ortho-para directing substituent, we get 2 products on electrophilic substitution reaction. One is the ortho product and the other will be the para product. Means the electrophile will come and attack ortho position, we get ortho product, plus the electrophile will come and attack para position, we get para product. Okay, now always para product will be the major product because of less steric hindrance. We know the para position is 1,4 position. So, we get para as the major product always because there is less steric hindrance in para isomer. Now, let's see what do you mean by ortho and para directing substituents? The substituents or groups which direct the incoming electrophile to ortho and para positions are called ortho and para directing substituents. Now, example for groups that show ortho-para directing property, that is amino group NH2, halogens, ether group. Then phenol is an ortho-para directing group. Then we have all alkyl groups like CH3, C2H5. All these are ortho-para directing groups. So, if any of these groups are present on the benzene ring, suppose if halogen is present or phenol is OH group is present, either OR group is present or CH3 group is present. Now, on electrophilic substitution reaction, we get ortho product and para product. Now, let's see an example for this. Here I have drawn the resonance structure of phenol. Now the question here is a very important question, why phenol is ortho-para directing group? So I gave example under ortho-para directing group, phenol is an example. Now the question is, why phenol is ortho-para directing group? For this, first you have to draw the resonance structure of phenol. Now the resonance structure of phenol I have drawn on the board. And you can see in the resonance structure, look at the ortho and para positions of the resonance structure. That is structure 2, this is the ortho position. Now, structure 3, we have a para position here. Structure 4, again we have another ortho position. Now, if you look at the ortho and para position, you can see in the resonance structure, there is more electron density present. There is more electrons present at ortho and para position. So, we know the electrophiles which are deficient in electrons can easily come and attack this ortho and para positions. So that is the answer. Why phenol is orthopara directing in nature? Because in the resonance structure of phenol, there is more electron density at ortho and para position. So electrophiles, which are electron deficient species, will attack the electron rich ortho and para position. So we get ortho and para product. Now we have in phenol OH group. Now OH group is electron withdrawing minus I effect group. Okay, this OH group is minus I effect group. It withdraws electrons from benzene ring. So there is decrease in electron density at ortho and para position of benzene ring, but the overall electron density increases at ortho and para positions due to resonance. So actually when you see this OH group present on benzene ring will withdraw the electrons from benzene ring. So we know that the electron density in the benzene ring decreases. But what happens is that in the resonance structure we can see more electron density at ortho and para positions. So we can say OH group is activating. OH group is an activating group and it activates the benzene ring, or it activates the electrolyte, the incoming electrolyte to ortho and para position. So OH group is an activating group. Okay, now the other examples for activating groups are this. There is NH2, halogens, ether, all alkyl groups. They are all activating group, means they activate the incoming electrophile to ortho and para position. Now one point you have to note here is about the halogens. Now when I draw chlorobenzene, I am not going to show the resonance of chlorobenzene. When you draw the resonance structure of chlorobenzene, again you can see electron density more at ortho and para position, and we know that halogens are ortho para directing substituents. Now this chlorine or this halogen, they are strong electron withdrawing groups compared with phenol OH group. Okay, so they show strong minus I effect. So we can say this haloarenes or halogens, they are deactivating groups. But we know that we get ortho and para products because there is more electron density at ortho and para positions in the benzene ring. So although these halogens are deactivating groups because of their strong minus I effect, we get ortho and para products when an electrophile attack due to high electron density at ortho and para position. So you have to be very careful with these substituents. Halogens are deactivating group due to the strong minus I electron withdrawing effect of halogens. Other groups, that is NH2, ether, phenol and all alkyl groups are activating group. But we get the products with halogen also as ortho product and para product. Okay, so this is one type of substituent, that is ortho and para directing groups. Now the second type of substituent is meta-directing groups. So first is ortho and para, second is meta-directing groups. Now what do you mean by meta-directing group? These substituents will direct the incoming electrophile to meta position. So they are called meta-directing groups. Now I am going to give example for meta-directing group. Nitro group, then SO3H, that is sulfonic acid group, and all carbonyl groups, carbonyl compounds. Carbonyl group is C double bond O. So carboxylic acid, COH contains C double bond O, aldehydes contain C double bond O, ketone contains C double bond O. So if all these are present on benzene ring, we get meta product on electrophilic substitution reaction. Same way we have nitro group, sulfonic acid group, all giving meta product. Now as an example and explanation, I have drawn here the resonance in nitrobenzene. And we know nitrobenzene is a meta-directing group, means we get only one product if the group is meta-directing, the product is meta-product. Meta position is 1,3 position. Now look at the structure of nitrobenzene. Now why nitrobenzene is meta-directing substituent, or nitro group is meta-directing substituent. Now look at the resonance structure. You can see in resonance structure number 2, we have a positive charge here at ortho position. Para position in structure 3, we have a positive charge, and structure 4, we have a positive charge again at ortho position. So positive charge shows deficiency of electron. We know who is coming to attack this nitrobenzene. It is the electrophile which are deficient in electrons. So they will not attack this ortho and para positions, because ortho and para position is not rich in electrons, whereas some electrons are present. Compared to ortho and para position, meta position is rich in electrons, so the incoming electrophile will attack the meta position and we get meta product. Okay, so this nitro group again, NO2, is a strong minus I effect electron withdrawing group. So what will happen? They are deactivating group. So as the strength of electron withdrawing group increases, minus I effect increases, the activating effect decreases. So we can say NO2 is a deactivating group because of strong minus I electron withdrawing effect of nitro group. Okay, so this is about the meta-directing substituents. So in meta-directing substituent, if present, then we get only one product during electrophilic substitution reaction, that is the meta product. So these are the two types of substituents, ortho and para-directing substituent and meta-directing substituent. In ortho and para-directing substituent, we get ortho product and para product, out of which para product is the major product in electrophilic substitution reaction. And meta-directing substituent, we get meta product as during electrophilic substitution reaction. And also we discuss the examples for groups that show meta-directing effect. Nitro group, sulfonic acid and all carbonyl group. These groups you should study, which are the meta-directing substituents and which are the para-directing substituents. Now, next I have written few questions here. Complete the following. These are all examples for the electrophilic substitution reactions. Now let's see the first question. We have chlorobenzene plus chlorine in presence of anhydrous aluminum chloride. So the first is halogenation. It's an electrophilic substitution reaction, and we know in halogenation, halogen is introduced into the benzene ring. Now here we have chlorobenzene. So chlorine is the substituent present, and we know halogens are ortho-para-directing substituent. So we get two products, one is ortho product and the other is para product, which means the electrophile chloronium ion we get it will get attacked to ortho position and para position. So how will you write the product of this? First we have this chlorine is this one and ortho position is this plus para position is this, and always write the word major under para. I told you always para is the major product due to less steric hindrance. Now next we have second question, chlorobenzene plus concentrated nitric acid and concentrated sulfuric acid is nitration. Now in nitration, nitro group is introduced, and we know again, look at the substituent is chlorine, halogens are ortho-para-directing substituent. So here also we get ortho product and para product. Now I am going to write the product. Chlorine, no change. Ortho product is this NO2 group. They will get attacked to ortho position plus para position, and always write the word major under para. Now the third question, C6H5OCH3, this is either group, ROR, either group plus CH3CO2iso is acetic anhydride in presence of anhydrous aluminum chloride. This is our Friedel-Crafts acylation reaction. and in acylation reaction, acyl group is introduced to the benzene ring. Now look at either. Either group is also ortho-para directing group. So we get two products, ortho and para. Now I am going to write the product. No change for. Now here in the question I have written OCH3 in this position, which means I have to write at the same position OCH3. Now ortho position is 1, 2 and COCH3 is introduced, plus the para product is, OCH3, don't change the position of the substituent. Para will be 1, 2, 3, 4. So this is para position. Here we will have OCH3 and write the word major under para. Now the next is number 4. We have acid group, benzoic acid plus bromine, again halogenation. So acid group, carbonyl groups are meta-directing. So we get meta product. So bromine will be introduced at third position. So how will you write the product? COH is given here. This is 1, 2, 3. So here we have bromine, this is meta. Only one product, meta. Now the last question is C6H5CHO, benzaldehyde. Again aldehyde group is the substituent and it is meta-directing. And here we have the nitration reaction, concentrated nitric acid plus sulfuric acid, and you know CO group. All carbonyl groups are meta-directing, so we get meta product, and in nitration, nitro group is introduced. So this is number 1, 2 and 3. We have NO2 here, meta-nitro benzaldehyde. Okay, so these are the examples for the directive influence of substituents. Now next we have one last question, that is we have 4 conversion questions. Let's do the conversion questions. The first question is conversions. You have to convert benzene to para-nitro-bromo-benzene. So here we have benzene. So this is our benzene ring. You have to convert it into para-nitro-bromo-benzene. 2 substituent groups are to be introduced. One is nitro and the other is bromine. Now, it is para-nitro-bromo-benzene. Now, we know that the nitro group is meta-directing and bromo group is ortho and para-directing. So, which one we have to do first? We have to do nitration or bromination first. First we have to do bromination to benzene. In that case we get ortho and para-bromo-benzene. And we know bromine is, first we have to do bromination, then to that you do nitration. Okay, we get para-nitro-bromo-benzene. So I am going to show this benzene plus bromine in presence of anhydrous FeBr3. You get ortho and para. Here you get one bromobenzene, not ortho and para. We get bromobenzene because we are converting benzene to para-nitro-bromobenzene. Now this bromobenzene, bromine is ortho-para directing. So next we are going to do nitration. So with concentrated HNO3 plus concentrated sulfuric acid, you will get nitro group is introduced. So we get ortho product plus para product, and we have to prepare para-nitro-bromobenzene, this one. Now ortho and para isomers can be separated by fractional distillation. So next you will write above the arrow fractional distillation. You get para isomer, that is So the name of the compound is para-nitrobromobenzene. Okay, so you have to check which electrophilic substitution you have to do first by looking at the substituents. Now the second conversion question is convert benzene to meta-nitrochlorobenzene. Now, meta-nitrochlorobenzene means the structure is like this. Meta is 1,3 position, meta-nitrochlorobenzene. So, here nitro and chloro, two substituents, one is meta-directing and chloro is ortho and para-directing. We need meta-nitro. So, first we have to do nitration, we get meta-nitrobenzene because the NO2 group is meta-directing. After that, when you do halogenation, that halogen will get attached to meta position. Okay, so I am going to write the conversion. Benzene on nitration, concentrated HNO3 plus concentrated sulfuric acid, you get nitrobenzene. Now this plus halogen in presence of anhydrous aluminium chloride. Nitro group is meta-directing, so you get NO2 Cl. Third position we have Cl. So meta-nitrochlorobenzene. Now third question is convert benzene to para-nitrotoluene. Now para-nitrotoluene is, the structure is this, NO2 and CH3. Para position is 1,4. Now here again we have two substituents, CH3 and NO2. NO2 is meta-directing and CH3 is ortho and para. So we need para-nitrotoluene. So which one we have to do first? We have to do CH3. To introduce CH3 we have to use Friedel-Crafts alkylation. So first do Friedel-Crafts alkylation followed by nitration. So I am going to write the conversion. Benzene plus CH3Cl in presence of anhydrous aluminium chloride. This is Friedel-Crafts alkylation. You get CH3 introduced to benzene ring. Now this is ortho-para directing, so do nitration. Nitration is with concentrated HNO3 plus concentrated H2SO4. Now here you get ortho and para products. CH3 NO2 plus ortho product plus CH3 NO2. This is para. Now how to separate ortho and para product? By fractional distillation. Now you get the para product first. This is what you have to prepare, para-nitrotoluene. Now the last conversion question is fourth one. Convert benzene to acetophenone. Acetophenone is the common name and the formula of acetophenone is C6H5COCH3. And you know how to introduce this acyl group by Friedel-Crafts acylation. We can use either acid chloride or acid anhydride. So I am going to write the equation. Benzene to acetophenone. Benzene plus CH3COCl in presence of anhydrous aluminium chloride, we get acetophenone plus HCl. So these are the four conversion questions. So with this we complete this chapter, that is hydrocarbons. Thank you.